Presentation of a dissertation entitled Explainable Cloud Forensics for Virtual Machines in Heterogeneous Distributed Data Centers. Content, introduction. Cloud computing is the delivery of cloud resources or computing resources over the internet in terms of software platform and infrastructure. People nowadays have adopted the cloud computing services because of the number of benefits that they offer. And companies have come in, as from this graph here, we see that Amazon Web Services is the most dominant company in terms of providing cloud-based services to the end users. This second graph here shows the cloud data center market growth, and is expected to grow, or estimated to have attained that is 69.45 billion US dollars by the end of 2033. And this other graph here shows the cloud incidents that have been registered as of 2024. So cloud computing is built on virtualization. The virtualization is the creation of multiple versions or instances or a replica of a given hardware or software to run on a single host computer. And now if you create very many virtual machines on a single host computer running different operating systems, and they are deployed in the cloud, and for public access, this one becomes a cloud computing environment. So a program called a hypervisor, it's a software that allows copies of the same computer system running different operating systems on a single host can be created. Cloud computing, cloud service providers use cloud data centers to provide cloud services for end users, and those data centers are distributed. They are distributed in order to allow users from those locations, geographical locations, to be provided with a number of workloads and to meet their different user needs. Cloud forensics is the use of scientific methods to identify, examine, collect, and analyze and report crime-related activities that have happened in the cloud environment. Much as the cloud computing cloud service provider offer a number of services, VMs are among the services that are being provided on the cloud, and those VMs are subject to a number of attacks. Yeah, they're subject to a number of attacks. So there are a number of cloud forensics methods that are used to detect, identify, and collect evidence from the virtual machines or from the cloud computing environment. So those cloud forensics systems or methods have the traditional ones like FTK, cross-view analyzer. They have challenges. One of them is they cannot penetrate the virtualized layers of abstraction. They rely on predefined database of known threats, and they are slow. They have high false positive rates and others. Then there are also existing deep learning forensics methods such as for example, the LSTMs. Those ones can be used to analyze and detect threats from the cloud computing environment, and specifically the VMs. But the problem with them They lack generalization ability. They cannot scale with the increasing volumes of cloud data, and they have delayed detection latency, and they lack explainability. Problem statement: existing cloud forensics methods have a challenge of scalability, and they have a challenge of detecting zero-day attacks. They cannot detect emerging attacks due to the fact that they are built in a database of known threats. Then they are slow. Detection latency it takes a lot of time to detect attacks and threats within the virtual machines that are distributed on a large scale that generate massive data. So it takes a lot of time when the cloud infrastructure grows. And then they lack explainability components that can be used for generating forensics reports and for decision making. Primary objective. So because of those challenges, they need to develop a scalable cloud forensics predictive framework that can be used by cloud forensics investigators to detect attacks from the logs, from the VM telemetry data. So the VM telemetry data you can use to train models so that we can flag out the attacked data or data that is infectious and data that is normal, attacked data and normal data. So the framework will be used will provide timely insights, enabling early detection of compromised VMs and supporting forensics investigations. Second objectives: to identify the status of the VM instances, to train, build, and evaluate deep learning models, and then incorporate explainability components by building explainers for sharp alignment, future permutation importance. Research contributions. The framework can be used by cloud forensics investigators to flag out VMs that are attacked and those that are not attacked. Then it can be used to correlate the patterns in the utilization of the patterns in the VM telemetry data to know that this VM instance is attacked because of maybe the increase in the spikes on the CPU utilization. So those signatures can be enhanced by explainers. So detailed comprehensive reports can be extracted. Then features that the model depends on to predict that certain VM instance is attacked can also be displayed. Key important features. So this other slide shows some little literature. I may not go through most of that content, but this paper here demonstrates an IGP model that was built to detect cyber attacks in virtualized environments consisting of a number of VMs. And it was built on four models, that is GAF, MTF, and CNN and LSTM. The challenges which this model had, it could not scale with the large-scale data from the cloud infrastructure that keeps on growing. Then the detection latency, and the model was also evaluated on known attack types, and therefore it was unable to flag out attacks that are changing. Zero-day attacks, it cannot flag out attacks that are coming from that are not part of the data set. Then they lack explainability components. Dataset description. So a Linux operating system was installed on the computer system of those specifications, and then Open Nebula cloud computing environment was also installed. 10 VMs were created. And then the LeafBird API virtualization library was used to extract VM log information from the KVM hypervisor that was used for model training. It consisted of 9,610 rows and 43 features. ADA. So from this ADA, we see that most of the VMs are normal, not attacked. Then the rest of the VMs, 20%, around 10% of the VMs are compromised. This heat map shows the correlation matrix. Correlation matrix, model building, training, and evaluation. So 10 deep learning models were built, and it is visualized from this graph that the best performing model are 4, that is feed-forward neural network, NN, TCN, and CNN, after performing a split of 80 to 20 for both training and testing respectively. Application of explainable AI. Yeah, I applied sharp, lime, and pimp explainability. So as you can see here, so these are line plots for the FFNN on these VM instances. So as you can see here, let me choose one graph here. From here, this 10th VM instance is attacked because of these factors. Moment last update. Even this one, it is attacked. This VM instance is 1,345 VM instances attacked. And these are the important features that demonstrate that this VM is attacked. That's the last update, time sys, time user, HDAT byte rate, etc. Now this is the application of PIMP on the feed-forward neural network. So here we see memory last update, time user, CPU time are the most important features. This is the application of sharp explainability. Model deployment and selection. So I chose the feed-forward neural network and it was deployed. It's one which I used to deploy on Render. So this is the pipeline shows from the model development to pushing the files to the version control system, then building a Docker image, Docker image, push to Docker Hub, retrieve from Docker Hub from Render, then access to a public URL whereby we imported the VM log data and then the VM, the model predicted that it is predicted the classes either normal or attacked. So this is the sample VM instance sampled from the dataset, uploaded dataset. That is, so this VM instance is normal, then this one is attacked. And these are the contributing features predicted by line, predicted feature importance. Conclusions. So the predictive model incorporated with explainability can be used by forensics analysts to know the attack indicators. For example, memory last update, we saw that's the most important, the most influencing feature. So spikes in the once the VM has too much data in its memory, it will cause that VM instance to freeze because there's very many processes are loaded into its memory, and those very many processes may be coming from a DDoS attack launched on that VM instance. So Lime explainability or sharp can be used by forensics analysts to know the attack indicators generated from the features. To understand why that VM is is attacked or normal otherwise. Limitations. The dataset is not annotated with specific attack type, and this may confuse cloud forensics investigators. Then SHARP and PIM consumes a lot of computational resources. That's why I didn't choose it for deployment, because it consumes a lot of computational resources. Future works. There's need to develop more datasets from other cloud computing platforms like OpenStack, Microsoft Azure, etc. And still, there's need to also annotate those datasets that have been developed from OpenStack and map them to their respective attack types. Yes, within from Open Nebula Cloud environment, cloud computing infrastructure. Then there's need to integrate computationally efficient explainability component models, computationally efficient explainability tools that not consume a lot of computational resources, such as integrated reagents, deep lift, such that they can also be explanations can be generated or returned after deployment. Thanks, Doctor. That's the end of my presentation. Thank you, sir.